This is section 1.23, forward biased p-n junction. So the p-n junction, we had the metallurgical junction, we had P on this side and N on this side. The P was doped with boron, and that means there's lots. We have a high concentration, or the holes is the majority carrier. And the N was doped with phosphorus, and we have a majority carrier, a high concentration of electrons. And so to forward bias it, we apply a potential, and this side is plus and this side is minus, and then we're going to have our depletion region where there's a lot of pluses here and a lot of minuses here, and that creates our E field, which is in this direction. And then our applied potential is going to be E applied in this direction. And so the net E field, we'll call E field net, is going to be in this direction. But the difference is from equilibrium state as this width has shrunk. So the width or barrier height has shrunk. So now electrons can go over here, and holes, we'll say little pluses, can go over here, and we have and the net effect is that we have a current flow. Whereas in the reverse bias case, we did not have a current flow, and we called this one, they called it VD, I guess, for voltage on the diode. And so this is the forward bias. And really the important thing in the whole section, if you get only one thing, is that we have this junction, and we have the minuses, and we have the pluses. Okay, remember these are the ions, they can't move. But now we have a gradient in the minority carriers. So on this side we have a gradient of electrons, and so what I'm drawing here is basically this is if the y-axis was concentration and the x-axis is distance. And on this side we have a gradient in the hole concentration. So the gradient in electrons on this side and the gradient of holes on that side. Now we have a diffusion current happening here on each side, and so that's what's generating the current in these p-n junction. It's the excess of minority carriers in the bulk neutral area of the p or the n type semiconductor. And so that's pretty much it for that section. Is that, we apply a field, it lowers the barrier, it allows the charge carriers to go across, which creates a gradient in the minority carriers, which causes the current. And see, the next section is 1.2.4, which is the ideal current voltage relationship for a p-n junction diode. Okay, so p-n, so I'll put this in parentheses, p-n junction diode. And So you apply a voltage, which results in a gradient in the minority carriers, which in turn causes these diffusion currents. And the equation that they present in the book, and again, like I said before, they don't derive these equations, is that the diffusion current is equal to IS, and this is the reverse saturation current. And this is a small number, something of the order of 10 to the minus 18th to 10 to the minus 12th. And times e to the Vd over, so this is a d in Vt, so that's the thermal voltage. And all of this minus 1. Okay, and so that's the relationship for the diode versus applied voltage across it. So, you draw a diode symbol, and this is plus, this is minus, and this is Vd. And like I said, Vt is a thermal voltage, which was equal to 0.026 volts. And then N in the equation is called the emission coefficient, or idality, I guess, idality factor. And N is less than or equal to 1. I mean greater than or equal to 1 and less than or equal to 2. And N takes into account recombination in the depletion zone or space charge region of the p-n junction diode. And what they say in the book is for low current, N is approximately 2, and for at higher currents, so higher current, and they don't specify what the actual values are, N is approximately 1. And the book basically says from now on and forever, we'll just assume N is equal to 1. And then they just give a definition of the p-n junction diode. So it has a p-n junction, and it has non-linear rectifying current characteristics. So the important thing here is that a p-n junction diode is nonlinear, not like a resistor where V is equal to I times R. It has this other equation here with the exponential in it. And so now I'm going to work example 1.7 in the text, where they have a p-n junction diode, and they tell you that the temperature is equal to 300 Kelvin, and the reverse saturation current is equal to 10 to the minus 14 amps. And what they want you to do is find your diode current for a applied voltage of VD equals plus 0.7 volts and for VD equal to minus 0.7 volts. And so it's at this point, it's just plugging it into that equation of ID equals IS, which was 10 to the minus 14, and then putting in your exponential to 0.7, that's VD, over the thermal voltage, and we assume N is equal to 1 minus 1. And you get 4.93 milliamps, okay? And then likewise for VD equals minus 0.7 volts, you're going to get 10 to the minus 14th, e to the 0 minus 0.7, 0.0, whoop. 0.026 minus 1, and you'll get minus 10 to the minus 14 amps, which I would just call 0 amps myself. And so that's it for the that example. Pretty straightforward and simple. So we're going to move on to section 1.2.5, and this is the p-in junction diode. And the first part is they give basically a curve, and this axis is always ID, and this is VD is the axis. So remember on your p-in junction diode again, this is plus, this is minus, this is VD across it. And you're going to get something that looks like this if you plot out. For a forward biased, so we'll call this area over here forward biased region. And just for completion, we'll say P in, and the same thing I drew over there. Plus, minus is forward bias, and this is VD. And I already drew the symbol up there. And then they just have a couple of notes in the in that section, basically saying that your reverse saturation current is proportional to temperature, and also your thermal voltage is proportional to temperature. Remember, VT is equal to KT over E. And they also say that the reverse saturation current is proportional to Ni. And remember, Ni was equal to BT to the 3 divided by 2, E to the minus EG, that's that band gap energy, times 2 KT. And they basically say IS is doubles for every 5 degrees Celsius. And so what you end up getting is these curves where you have, again, ID, VD increasing that way, and then you get something like this, where this is T, some temperature, T2, T1, and T0, where T2 is greater than T1, which is greater than T0. So as the temperature increases, you need less voltage to get the same current. Let me double check that. Yeah, that's correct. So as the temperature goes up, then T2 needs less, you need less voltage to get the same current. Then they go into breakdown voltage. Breakdown voltage. Where that's where you have a PN junction diode, PN, and you have it in a reverse bias configuration, where this is plus and this is minus. And they're saying if when VR becomes too big, then covalent bonds are broken, and electron/hole pairs are formed. And so you get these electron-hole pair are formed in the PN junction, and then current can start to flow. And so you have VD again, ID, and we have our forwarded bias area. And then in reverse bias, you can get a current happening if you hit the breakdown voltage. We'll call this breakdown voltage 1 and breakdown voltage 2. And 1 happens at lower voltage because it's highly doped, and 2 happens at a higher voltage because it's got low doping. So the concentration of the dopants that you add is less. And they give some mechanisms. One they call is the avalanche breakdown. Okay, and this is where carriers, so that's your electrons and holes, enter the depletion region, or space charge region, and they have enough kinetic energy, so their kinetic energy is high, that they break the covalent bonds and generate more holes and electrons. So you get more holes and electrons, which then they gain kinetic energy and break bonds and generate more, and so forth and so forth. Hence the name avalanche. And then that's one of the mechanisms they talk about. And then the other one is called the Zener breakdown, where this consists of carriers tunneling across the junction. So that would be some type of quantum mechanical effect. And this happens at high concentrations, high doping concentrations. And they say in there that the breakdown voltage can be less than 5 volts. And so later on in the end of the chapter, they talk more about this Zener diode. And the last for this particular video is they talk about switching a transient. Okay, and so a transient response is the so you could say the transient response consists of the speed and say characteristics as it no, we'll see, not as the p-n junction diode is switched from one state, and by state I mean on or off, to another state. So it consists of the speeding characteristics as the p-n junction diode is switched from one state to another state. And the example that they give is we have a forwarded bias diode, and it is on, and then we switch it off. And so when it's on, you have something that looks like this. Say we got an RF, some type of resistor in there, and then we have our p-n junction diode, p-n, okay, plus minus VD, and then we'll make this go to ground, and this is our power supply, V forward there, VF on the power supply. So if you just do KVL, that's Kirchhoff voltage, you'll get minus VF plus, and if we call this a current flowing through it, IF, RF plus VD equals 0. Then IF, which is essentially our I diode, is equal to VF minus VD over RF. So again, just to remind you, under forward bias conditions, you have an excess of minority carriers. So forward bias, excess minority carriers, okay, when something's forwarded bias. And then when you switch it off, you need to remove this excess. Well, not you, but the excess minority carriers in each region need to be removed. So under reverse bias, so this is after we've switched it off, then our p-n junction is going to be in this situation, p-n, and then we have the resistor, that RF, and then we're in a reverse bias situation where we have this is minus and this is plus. Okay, and we'll call this V reverse. And the thing is that ID at this point is going to be limited to, and we'll call this IR, minus IR, which equals minus VR over RR. So ID is going to be limited to this value by these parameters here when you switch it off. And the current cannot instantly go off because of we have these capacitances in here. And remember that the current from a capacitor is equal to C times dV dt. So the voltage cannot actually go off instantaneously either. And so this current IR is essentially constant for in the book they say T minus TS, where they call this the storage time. So this storage time is the time it takes for the excess minority concentration to be removed. Because remember, as I drew before, you have your p-n junction, and we have this excess of minorities, and this has to go away. And so once you flip it off, and the time that it takes is this storage time. And so they have this graph of ID versus VD, and so you have it on, and you call it ID, and then when you turn it off, we have the storage time. We call this minus IR, and so we have this storage time. And then after the charge is the minority carriers have went back to where they should, then actually this is not voltage, this is time, sorry. We're talking about time now. Time. And so we have this storage time where the current's essentially constant. Then when the minority carriers get back where they belong, then it kind of falls off, and we call this the fall off time. Fall off time. Okay. And so your total turn off time is going to be equal to the storage time plus TF, how long. And fall off time is basically the time that it takes for the current to reach 10% of minus IR. So 10% of its starting value.